Okay, lastly, in chapter 3, we're looking at how numbers can deceive, how it matters how you look at the numbers, how you interpret the numbers, because that can make a difference in how you make decisions moving on. So, let's look at batting averages. So, let's compare major leaguers Derek Jeter and David Justice in 1995 and 1996. And we're going to look at the years separately, and we're going to look at the years together and see how those numbers differ. So, which player had the higher batting average in both 1995 and 96? Well, we see that in 1995, Jeter had a batting average of .25. Justice had a batting average of .253. So Jeter was better Justice was better in 1995. In 1996, Jeter got a .314 and Justice got a .321. Again, Justice was better in both 1995 and 1996 separately. Okay, well, now let's look at the 2 years together. So to get the batting average, you take the number of hits and divide by the number of at-bats. So we need the total number for 1995 and 1996. So Jeter, to get the total number of hits, you're just going to add these two numbers, so 12 plus 183. And we get 195. At bats, we have 48 in 95. We have 582 in 96. So that gets us a total of 630 at bats. So that means Jeter's average is going to be 195 divided by 630, which gives us a .310. Justice have 104 plus 45. That's 149 hits. We take 411 at-bats and add on the 140, and we have 551 at-bats. So his average, we have 149 hits. I have a total of 551 at-bats to give him an average of .270. Okay, so we see that Justice was better in 95, 96 individually, but we see Jeter is actually better overall, which was the answer to part C. So why is this the case? Why are we getting two different answers for who's the better player? And what really matters here is we got to look at the numbers that gave us these percentages. So percentages and averages, they can be great, but when you're comparing two things, you also have to, when you look at like combining things together, you have to look at the individual makeup. So for example, well, just as a brief refresher, so we know that Justice was better in both categories, 1995 and 96, but together Jeter scored better than Justice. And this is because if you look at the numbers of at-bats and hits, you see that Jeter has a lot of hits on this higher average, whereas Justice's most of his hits were in at-bats. That was his lower average. So when you combine them together, Jeter's higher number with more hits contributing to the higher number is going to make him be the better one overall. Okay, now let's look at tuberculosis deaths, comparing two cities and the percentages there. So let's look at the deaths due to tuberculosis or TB. Let's look at the death rate. So death rate is going to be the number of deaths per population or per person in their population. So if we want to look at for whites, non-whites, and all residents of New York City, for whites, there were 8,400 deaths out of a total of 4,675,000 whites. So the death rate for whites is 0.0018. And the death rate for non-whites, so this is the number of deaths per person for all of these. So for non-whites, you had 500 deaths out of a total of 92,000 people, 92,000 non-whites. So out of 92,000, 500 of them died, and that gives you a death rate of 0.0054. Now you can put these in percentage points or percentages if the problem asks for a percentage, and if it does, it'll have the percent sign right after the text box. If it doesn't have the percent sign, then you can just leave it as a decimal. Okay, so non-whites are 0.0054 deaths per person. Now, if we look at the total, there's 8,900 deaths out of a total population of 4,767,000 people. So we find this one. So overall, there is a death rate of 0.0019. Okay, so now let's look at Richmond, Virginia. So we look at whites, 130 deaths out of 81,000 total, which gives a death rate of 0.0016. For non-whites, we have 160 deaths out of a total of 47,000, which gives you a death rate of 0.0034. And then overall, we have 290 deaths out of a total of 128,000, which is 0.0023. So in comparing these, if we look at the tuberculosis rates in each category, so whites and non-whites, comparing New York City and Richmond, Virginia, for whites, we have 0.0018 and 0.0016, so New York City has a higher number. For non-whites, New York City has 0.0054, Richmond is 0.0034. So again, New York City has a higher death rate for both whites and non-whites than in Richmond. But if we compare the overall New York City is only 0.0019, and Richmond is 0.0023. That was higher in Richmond. Okay, so why is this? So with the last example with Jeter and Justice was because you're looking at like the number of at-bats. Well, here, let's look at the difference between whites and non-whites. So we look at the difference in population here in New York City, and we have so many more whites than non-whites. And then in Richmond, they're a lot closer together. I mean, there's like twice as many non-whites or whites as non-whites, but I mean, this is way more than just twice as much, right? So here you have the bulk of them as 0.00 or 0.0018, which is a lower number. But here, because they're a lot closer together, it doesn't make as much of a difference. So overall, you're going to have 0.0023. So you can read just a summary of that here. Okay, now let's look at test results. So women go in for mammograms. And so the mammogram is meant to see whether the tumor is a cancer or not. And so we're going to use this table to help us figure out like the chances of having cancer with positive or negative results. So this table is based on the assumption that 1% of breast tumors are malignant. So if we're going to take, for example, a total of 10,000 tumors, so 10,000 people who have had a lump in their breast, they go and get them checked out. So we're saying that 1% of breast tumors are malignant, which means that so 1% of breast tumors, so we have 10,000, so we have 1% of the number of tests or the number of tumors we have gives us 100. So out of the 10,000 tumors that we have, 100 of them are going to be malignant, which is where they get this number here. And then, of course, if 100 of them are malignant, that means 9,900 of them are going to be benign. Okay, so these screenings are typically presumed to be about 90% accurate for both positive and negative, meaning they'll correctly give you a positive result in 90% of cases, and correctly give a negative result in 90% of cases in which there is no cancer. So what that means is 90% of those who have cancer, the test is going to show it. So of these 100 people who actually have cancer, 90 of them are going to show up as a positive test. 10 of them are going to come back negative. Of the 9,900, 90% of these are going to show negative, that it is benign, so accurate there, and that is 8910. And then the remaining 10% is going to be give you a positive result. These numbers here just come from adding up these. So the total number of positive mammograms in these 10,000 people are the 90 plus 990, which is 1080. So out of the total 10,000 cases, 1080 of them give a positive mammogram and 8920 will give a negative mammogram. And so we have these terms here: true positive, meaning that it gives you positive and it's true that it is malignant; true negative, meaning that it is negative and it actually is benign; false positive means it says it's positive, it says it's cancer, but it's not. This one is negative, it says it's not cancer, but it really is. Okay, let's look at some percentages here. So suppose a patient has a positive mammogram. What's the chance that she really has cancer? So you go and you get tested and it comes back positive. Well, we know the test is 90% accurate, but does that mean that you have a 90% chance of having cancer if you have this positive mammogram? Well, this, we're going to use a part out of a whole. Now, we don't have the of here, but we're definitely not comparing, so it has to be this. So this, suppose, takes the place of our of, which is going to be your whole value. So the whole value, suppose a patient has a positive mammogram. So we want to look at how many positive mammograms we have. Well, 90 of them are malignant, 999 or 990 are benign. So total, we have 1080 positive mammograms. So when asking for a chance, that is your part. So what's the chance that she really has cancer? So you have a positive test and you have cancer. So the number of people who are positive with cancer are these 90 here. So if we want the percent, that chance, we were part, so how many of all of the ones that tested positive actually have cancer? So 90 over 1080, and that gives us a 0.083 or an 8.3%. So what this means is that if you test positive, there is an 8.3% chance you have cancer, which really isn't that high of a percentage. So just because you're positive doesn't mean you have cancer. It means there's going to be more tests. So similarly, what is the chance of a positive mammogram given that the patient has cancer? So in this case, given is another word for suppose. So this is going to be your whole, that the patient has cancer. So out of all these cases, how many have cancer? Well, that's this malignant tumor. So the total number of tumors are 100. And the chance gives you your part. So the positive mammogram. So we want cancer and positive mammogram. So again, that is this 90 here. So to get the chance, we're going to take our part and divide it by the whole. So you get 0.9, which is 90%. So what this means is if you have cancer, there's a 90% chance the test will catch it. Which is good news, right? So if you have the cancer, you want it to catch it. So people think that, so you have to be careful with the 90% accuracy. It means it's trying to catch all of the cancers. And so because it's trying to catch all the cancers, sometimes it catches things that aren't actually cancer, but they want to make sure that if you do have cancer, they catch it. So part C, suppose a patient has a negative mammogram. What's the chance that she actually does have cancer? So this would be your false negative, saying, so you go in, you get it tested, it says you don't, but they're wrong and you actually do. Now this is something you do not want to happen. So hopefully this is a small percentage. So or suppose our patient has negative mammogram. So this is your whole, is your negative mammogram. So go back up here, and total number of negative mammograms is 8920. So the chance gives us our part. He actually does have cancer. So negative and cancer. So how many people are negative but do have cancer? That is 10. Okay, so to get the chance, I take the number who are negative with cancer, which is 10, over the whole, which is 8920, total number of negative mammograms. We do that division, and we get a 0.001, or a 0.1%. So if you have cancer, I'm sorry, if you have a negative result, so if your test comes back negative, there's only a 0.1% chance that you do have cancer. Which is a pretty low percentage, which is good. Okay, let's look at another test result. So this time we're just looking at a basic disease. We don't really care what it is. Let's say that this disease test is again 90% accurate for those who have the disease, or true positive is 90% accurate for those who don't have the disease. So just like we did before. Within a sample of 2,000 patients, the incident rate of the disease is the national average, which is 2%, which means that of these 2,000, 2% of those actually have the disease. So if you find 2% of 2,000, you're going to end up getting 40, which is where you get here, which leaves 1960 of them that don't have the disease. 90% accurate says that if they have disease, it's going to test positive. So 36 is 90% of 40, with 4 left over. Same thing here, negative with no disease is the accurate one. So this is 90% of the 1960, and this is the remaining. Add these two to get these total. Okay, so of those with the disease, what percentage test positive? Now this one's a little bit easier to see that it is a part of the whole because it does say of. So again, of those with the disease, that means that is your whole, and the percentage test positive. So test positive is going to be your part. Now remember, the part includes both the category that says whole and what it says here. So we want, for the part, it's going to be the number that have the disease and test positive. So the number that test positive and have the disease is 36. Out of everyone who has the disease is 40. So percent is going to be 36 out of 40, which is 0.9 or 90%. So again, if you have the disease, 90% chance the test will show positive. Another way to say it. This one isn't quite asking for a chance. This one's just saying how many tested positive. So 90% of everyone who have a disease tested positive. Okay, so of those who test positive, what percentage have the disease? So here we're flipping it. So of those who test positive, so now those who test positive is the whole, because you have this of here, percentage have the disease, that is your part. So the whole, so everyone who tested positive, so of all those who tested positive, we have 232 total. And then who have the disease. So those who test positive and have the disease are 36. So now to get that percentage, we take the part and divide it by the whole. So 36 divided by 232, and we get 0.155 or 15.5%. So the difference between this one and this one is if you test positive, you have a 15.5% chance that you have the disease. So here for A, you're focused on everyone who has a disease and if the test catches it. For B, you're more concerned with those who test positive, what the test means for about the disease. If a positive test does actually mean you have the disease. Okay, last example. Of those who test positive, what percentage do not have the disease? So now we're actually talking about like the opposite of this one. So of those who test positive, for B, we found those who have the disease. Now I want those who do not have the disease. So again, those who test positive is going to be the whole. So we have 232 people, just like we did before. Now those who do not have the disease. So how many people tested positive and didn't have the disease? So test positive, no disease, that's 196. So we have the part, which is 196 divided by the whole. And this we get 0.845 or 84.5%. So if you test positive, there's an 84.5% chance you don't have the disease. So it's the same thing for this test as well as mammograms. If you get a positive result, most likely it is a false positive, but there is still a chance that it is true. However, if you you can also pretty much trust the negative. If you don't have it, it's a pretty good indication that you don't have the disease or you don't have cancer. But if you do have it, you should feel comforted that it should catch it. Oh, or the test should catch it. Okay, if you have any questions, let me know.